Hello everyone. So we have seen the matter wave and also the radiation pressure and photoelectric effect. We have completed all that, and today in this lecture of crash course we will complete atomic structure. Okay, the speed will be little bit fast because we have to cover all the things in this crash course before your exam. So in this lecture I will be telling you all the things, important things only. Many formulas are there, but I will not tell you that are not that important, and now that you cannot remember that. So all the important things I will tell you in this complete atomic structure, what you have to remember, what you have to keep in your mind. Okay. After that, not in this video, next video I will be bringing questions. Last 3-year JEE mains problem, I have discussed that. Please watch that. If you are watching this complete crash course, then please watch that. And if you are preparing for medical, then I have separately made a video for last 3-4 years NEET problems. Are you getting my point? I am not mixing that question in this lecture because some of you are from looking for your IITJEE mains, and some of you are looking for NEET medical. So that's why in this complete theory I will be teaching you. After that, questions I have made a different video. So please have a look in that with that also. So let's start the atomic structure. Atomic structure, you must have read something about this in chemistry. Okay, in physics we know that atoms are there. In that atom, what is happening? There is a nucleus, electron, proton. Now we know that, but what are the history about that, how we got to know? So let's we will just look a very fast in very speed. The first model that is given by J.J. Thomson, what he said, that atom is like a watermelon. Atom is like a watermelon where that seeds are negatively charged. You can see the image where that seeds are negatively charged and all the rest is positive charge. Okay, so that is, this model is given by J.J. Thomson. After that, who came? Rutherford came. He did an experiment. He has taken a very thin gold foil. Okay, very thin gold foil. See here, very thin gold foil, and then alpha particles were embedded on that with a very high speed alpha particle. Then what result he has seen? What he has seen is 99% went undeviated. 99% of the alpha particles that are coming has crossed undeviated. Okay, here this complete screen that you are looking is sensitive to alpha particle. When alpha particle is striking to that, they are becoming bright. Okay, so because of that we are able to see where these alpha particles are striking. Are you getting my point? So what he said there, he has seen the conclusion from this experiment has came that 99% of the alpha particle has went undeviated. That means straight. That means there were no objection in between. No one is deviating its path. 0.1%, 0.14% by 1 degree or more, very less, 1 degree or more, they have shifted. And only 1 in 10 raised to power 6, out of 10 raised to power 6, only one particle is there which has came back, which is deviated by 180 degree, which is deviated by 180 degree. Are you getting my point? So from all this, he concluded that there is mass is concentrated only inside, in some part. Other 99% of the part of the atom is free. Space is there. Are you getting my point? Mass is concentrated on the center and electrons are revolving around. Are you getting my point? So this is Rutherford atom. What he said, that all the positive charge and the mass is concentrated inside. Rest electrons are moving around that nucleus. Are you getting my point? So this is the Rutherford model of atom. Now after this, he has also calculated the minimum distance of approach. That means approximately radius of nucleus. How he did all the calculation we are not going to see. Just a very simple idea I am giving you and the result that you have to remember. Are you getting my point? So distance of closest approach. Distance of closest approach. What he did, he has taken an atom of atomic number Z. So how many proton will be there inside? Ze. Charge will be there, and alpha electron with very high kinetic energy has directed towards this atom. Then what will happen? This atom is there, alpha particle, positive charge. See here. Okay. So what will happen? This positive charge and this positive charge will repel each other. Yes or no? Like charges repel each other. So they will repel each other. Now this alpha particle, see, this alpha particle is having a very high kinetic energy on this direction, velocity, but having a force in this direction, opposite direction. So what will happen? Its speed will decrease. Its speed will decrease, and after some point, its speed will become zero. After some point, its speed will become zero. Are you getting my point? Again, I already told you that electrostatic force is a conservative force. Electrostatic force is a conservative force. So you can apply total mechanical energy will remain constant. Initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. So from that equation, we have found the radius. Okay, and now how we have found that? We know that if more kinetic energy will be there, R naught will be less. This distance I am telling you that R naught, the distance after which this electron will stop. So from the nucleus, how far this alpha particle is getting stopped, I am telling it R naught. If you have given a very small kinetic energy, then that particle will travel very less and stop. So R naught will be more. This path will be less, then R naught will be more. That means if you increase the kinetic energy, your R naught will become less. Are you getting my point? So what is happening? According to NCERT, the maximum kinetic energy that this alpha particle can have naturally is 7.7 mega electron volt. Are you getting my point? This is a NCERT data. Somewhere it is in some different books, different author, some little bit different magnitudes are given. But we will go with NCERT. In NCERT, what it is said, maximum kinetic energy of this alpha particle naturally that is possible is 7.7 mega electron volt. So according to this, when kinetic energy is maximum, your R naught will be minimum, and that R naught is calculated is coming 3 into 10 raised to power minus 14 meter, or you can say that 30 Fermi, You have to remember this. You can remember this. Are you getting my point? What is the maximum kinetic energy that this alpha particle can have? 7.7 mega electron volt. And this equation I already told you, kinetic energy initial plus potential energy initial equal to kinetic energy final plus potential energy final. Are you getting my point? From that equation we have got this R naught, distance of closest approach, or we are saying approximately radius of nucleus. Approximately we are getting radius of nucleus. Are you getting my point? So this is also the experiment by Rutherford. What are the drawbacks? There is a drawback of this Rutherford model. What are the drawbacks? Okay, just tell me, what are the drawbacks? Just disappeared. Okay, so let's see what are the drawbacks. What it is said that these electrons are revolving around the protons, okay, nucleus, around the nucleus. So when this is having an acceleration, so when there is a electron is accelerating, then this electron must radiate energy, and if these electrons are radiating energy, then its energy must loss, and this electron must collide with the nucleus, which is not happening. We know that, okay, today everything is existing because this is not happening. This electron is stable. So this stability is not explained by Rutherford. Rutherford was not able to explain why these electrons are stable. According to his theory, this electron must lose energy and become unstable. But that is not happening. We all are living here. This electron exists, atom exists. Are you getting my point? So this was the first drawback. What is the second drawback? When any gas is heated, okay, so radiation came out. When that radiation is seen, it is having only specific wavelengths, not all discrete, complete. It is having very not continuous wavelengths we are getting. We are getting only some wavelength. For example, 700, then 750, then 800. Are you getting my point? We are not having each and every. But what he said that, Rutherford said that electron can revolve in any radius. If electron can revolve in any radius, then we can get any wavelength. But that is not happening. So this was the two major drawback of Rutherford. Are you getting my point? So for this, now who came? Bohr came. 1913. At 1913, Bohr gave his model. What he said that these electrons, are not revolving in any random orbit. They are revolving in a very specific orbit. What they are saying? What he said, Bohr said that these electrons are not revolving anywhere just randomly. they are revolving in some particular orbit, in which all this orbit have a fixed energy. All this orbit have a fixed energy. Are you getting my point? And he named that orbit as K, L, M, N, like that. Are you getting my point? What are the drawbacks of Rutherford? Two drawbacks. For that, who came? Bohr came, 1913. And he said that these electrons are not revolving in any random path. They are revolving in some particular path, specific orbit. And that orbit have some fixed energy. And the electrons that are revolving in that path, in that orbit, have same energy of that of orbit. And he named that K, L, M, N, O. Are you getting my point? Like that. So this is the first thing. Electron has same energy as that of orbit in which it is revolving. I already told you. After that, what he said that this is, now you are looking into a very, very, very small thing. There you cannot apply that classical physics. What he said? Grow up, man, grow up. You cannot apply all that classical physics into such a small thing. You have to apply quantum physics, quantum mechanics, quantum physics. And here in this world, in this small world, quantum physics, everything is different from classical physics. What he said? Here, when these electrons are moving, he is not liberating the energy. Explanation: it is a quantum physics. Here, this only happens. Are you getting my point? So that was the point from where this has started, all this quantum, that when you are looking into very, 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 very small, quantum means very, 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 very small. At that point, this classical physics is not applicable there. For that, different research and all things are going on. Quantum physics. Are you getting my point? Okay. So what he said, these electrons are not revolving in any random. They are revolving in some specific orbit having some specific energy. And when this electron are revolving here, they are not losing energy. Don't apply your classical physics. This is new quantum physics. Are you getting my point? Also, he defined this stable orbit. How he defined this stable orbit is important. What he said, that angular orbital momentum of electron must be equal to integral multiplication of h by 2 pi. Integral multiple of h by 2 pi. Where h is your what? Planck's constant. You know that h is equal to Planck's constant. We have already used it. So what he said, that angular orbital momentum of electron is only multiplication of integral multiplication of h by 2 pi. So what he said, that what is angular momentum? mvr. We have already seen that. What is angular momentum? m into v is momentum. For angular momentum, what we are doing? mv into r. When mv and r are perpendicular to each other. So we are taking that it is a circular orbit. So for circular orbit, orbital angular momentum is mvr. So we have equated mvr with nh by 2 pi, where n denotes your orbit. When you are in the very inner state, n equal to 1, then second, n equal to 2, third orbit, n equal to 3, fourth orbit, n equal to 4. Are you getting my point? Everything? Okay. So this is the first equation. You can see n denotes orbital number k, l, m, n. That means k is the first, l is the second, m is the third, n is the fourth. From here he got the first equation. That means, you know what, we are going to derive something. Okay, so let's see. Now, this is the first equation. What he said, all these things are said by Bohr in 1913. What he said, that electrons are not moving in any random, they are moving in a specific orbit having a specific energy. And the electron moving in this orbit has that same energy of the orbit. And this orbit, what he defined, that this orbit are such that its angular momentum is integral multiple of h by 2 pi. From there we got the first equation. Now, what he said, that Bohr's quantized momentum, according to this, what he said, that okay, first thing, if anything is moving in a circular path, there must be a force, centripetal force. Who is giving the centripetal force? Electrostatic force. There is a charged electron and there is a charge in a proton. So this proton and electron is having a force. Because of this positive and negative electron, there is having a attractive force, due to that attractive force, these electrons are moving. These electrons are moving. So what he said, that centripetal force is given by mv square by r, and which he equated by electrostatic force kq1 q2 by r square. Are you getting my point? So this is equation 2 and this is your equation 1. From these two equations, what he got is a very big formulas that you don't have to remember. What you have to remember is, after in that formula, after putting all the values of z, e, and everything, okay, everything when we have put it in that equation, value of h, e, everything in a proper unit, length, meter, everything, then we got some result, and you have to remember this result. I'm not giving you any of that formulas because that you don't have to remember. What you have to remember is radius of any orbit in any atom. Are you getting my point? Radius of any orbit in any atom is given by 0.529 n square by z, where n is orbital number. Where n is orbital number. If it is the first orbit, very near to nucleus, first orbit, then n equal to 1. When it is second orbit, then n equal to 2. When it is third, then n equal to 3. When it is fourth, n equal to 4. Are you getting my point? And what is Z? Z is the atomic number. For hydrogen, Z is 1. For helium, Z is 2. Helium plus. For lithium, Z is 3. Are you getting my point? You are aware of all this. You are reading chemistry also. Either you are preparing for engineering or medical. Is this clear? Is this clear to everyone? What you have to remember is radius. Radius of any orbit is given by 0.529 n square by z. N square by z. Simple. How we got this? From two equations. One is Bohr model equation, where he said that angular momentum is equal to integral multiple of h by 2 pi, and the second from our dynamics of circular motion. If any particle is moving in a circular motion, there must be a centripetal force which must be equal to mv square by r. So from these two equations we have got this result, that r must be equal to 0.529 into n square by z. Similarly, the velocity of that electron is given by 2.19 into 10 raised to power 6 z by n. That means when n is increasing, that means you are going away from nucleus, your velocity will decrease, and the velocity is maximum for the particle which is very near to nucleus. That means the particle which is in the ground state. Okay, I will tell you, in the first state. First state means very near orbit. Are you getting my point? All these things clear. Only you have to remember these formulas. R is equal to 0.529 n square by z. What is your velocity? 2.19 into 10 raised to power 6. 2.19 into 10 raised to power 6 z by n, where z is atomic number and your n is orbital number. Now total energy is minus 13.6 z square by n square. Minus 13.6 z square by n square. Why we are keeping negative? I think I have told you this in current electricity also. At infinity we have taken potential 0. At infinity we have taken potential 0, and potential energy at infinity is 0. So from there, when we are bringing here, it is having negative energy, because negative work done you are doing. Negative work done you are doing. Are you getting my point? Is it clear to everyone? Okay. Now one more thing I am telling you, if total energy is this, okay, just remember first this R, V and total energy. What is R? 0.529 into n square by z. What is V? 2.19 into 10 raised to power 6 z by n. What is total energy? Minus 13.6 z square by n square. EV. This energy is in EV, electron volt. Electron volt. I have already told you electron volt is a unit of energy. Are you getting my point? You can write it down. Very important. These three formula you have to remember. And one more thing, this all things is valid for H-like atom. We have only derived it for one electron, when one electron is revolving outside. Okay, so only for H-like atom, that means H atom, helium plus, lithium 2 plus, 2 plus means 2 electrons gone. The only one electron is left. Only valid for H-like atom, remember. Done. Okay, now just remember one thing that I am telling you, very important. This is important now. If total energy is minus x, if total energy is minus x, okay, I'm writing here somewhere. Okay, here. If total energy is minus x, then your kinetic energy will be x. Just remember, I'm telling you, if your total energy is minus x, that means the kinetic energy that the electron is having is x, and the potential energy that electron is having is minus 2x, minus 2x. So you can see kinetic energy plus potential energy is your total energy, so x minus 2x is minus x. Are you getting my point? So if in any question it is given that total energy of electron revolving is minus 3.4 eV, what is kinetic energy and potential energy? What you will say, kinetic energy is 3.4 eV. Kinetic energy is 3.4 eV. What is potential energy? Potential energy will be minus double of this, 6.8 eV. Are you getting my point? It is very simple. Just remember, what is the total energy? Same will be kinetic energy, only plus, in plus. Okay, and what will be the potential energy? Double of total energy, double of total energy, in negative. Are you getting my point? Very simple. If total energy is minus x, then kinetic energy will be x and potential energy will be minus 2x. Simple. A very simple example. If total energy is minus 3.4 eV, then what is kinetic energy and potential energy? So you can simply say that kinetic energy is 3.4 eV and potential energy is minus 6.8 eV. Are you getting my point? Is this clear? Okay. Very good. You can see here n equal to 1, this is n equal to, sorry, this is n equal to 1, this is n equal to 2, and this is n equal to 3. Different orbits are there, no, not random, only specific, first, second, third. What do you name that? K, L, M, and the next is N, like that. Are you getting my point? Is this clear? All these three formulas clear? Remember, can you remember this? You have to remember this. Now, not can and all. Next, we have defined some states. When n equal to 1 is there, we define it as ground state. We defined it as ground state. Are you getting my point? N equal to 1 is known as ground state. N equal to 1 is known as ground state. So for ground state, energy, if you want to write total energy, what will write? Minus 13.6 z square by n square. Now for H atom, your z is 1 and n is 1. We are talking about the ground state, then n is always going to be equal to 1 for ground state. Now z is 1. Z is 1 means for H atom, when you put here instead of z 1, instead of n 1, what you will get? 13.6 minus 13.6 eV. That means for H atom in ground state, total energy is minus 13.6 eV, not joule. Unit is eV, electron volt. If you want in joule, just multiply it by 1.69 into 10 raised to power minus 910. 1.6 into 10 raised to power minus 910. Are you getting my point? Then you will get in joules. Very good. Now for helium plus atom. For helium plus atom, n is going to be equal to 1, but atomic number is 2. Z is equal to 2. So when you will put here 2 2s are 4. So 13.6 divided by 4 is minus 15.4 eV. You can remember this 13.6, other you can calculate in exam. It's not that big task. Are you getting my point? Whatever you have to remember, I will tell you. Don't worry, I am here with you. Now next, excited state. Okay, first excited state means n equal to 2. When electron is in second orbit, when electron is in second orbit, we are saying that electron is in first excited state. When electron is in third orbit, we are saying that electron is in second excited state. Okay, when n is equal to 2, then we call it first excited state. When n is equal to 3, we call it second excited state. Is that clear? Now, ionization energy. What do you mean by ionization energy? You must have heard it in chemistry also. What do you mean by ionization energy? When you are taking out electron from first state to infinity, then the minimum energy that you require is known as ionization energy. Ionization energy is the minimum energy required to take an electron from its ground state to infinity. From its ground state to infinity. Are you getting my point? Similarly, ionization potential, the potential that you need for that, simply instead of EV, just divide it by E, you will get the potential. For example, if ionization energy is minus 13.6 eV, then potential is minus 13.6 volt. Simple, very simple. Now what is excitation energy? Simple. Excited state is there, simply excitation energy. If you want to take electron from one state to another state, then the energy required is known as excitation energy. Then the energy required is known as excitation energy. Okay, now it is coming binding energy. What is the binding? What was the ionization energy? You are taking electron from ground state to infinity. That was ionization energy. Now binding energy is electron is not in ground state. It is in already in some other state. So from there you are taking it to infinity. So that is known as binding energy. That is known as binding energy. You are taking it from n equal to n to infinity, from some state to infinity. Clear? Okay, now this is a spectrum. Okay, emission spectrum. Emission spectrum means when that wavelength radiation is occurring, then what wavelength you are getting, we are categorizing it. Okay, so whenever any radiation that is happening, that is taking place when electron jumps from any state to ground state, from any state to ground state, where it is coming to ground state, n equal to 1, that series is known as Lyman series. That is series is known as Lyman series. For example, I have already made it here. For H atom I am talking about. This is first state, n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. So much energy is required here, more than the live class, more than the face-to-face class. Here energy is required. So just 2 minutes. Chalo. Okay, so let's see. Mic is there. Hello. Okay, so what I'm saying is, any wavelength, any radiation that is coming when any electron is jumping from any state to n equal to 1, from any state to n equal to 1, then that series is known as Lyman series. And when electron is coming from any state to n equal to 2, to n equal to 2, coming to second orbit, from any state it is coming to second orbit, then that all wavelength is coming in Balmer series. Similarly, when any radiation is occurring when electron is jumping from any state to n equal to 3, then that is known as Paschen series, then bracket, then Pfund series, like that. Are you getting the point? Now one very interesting thing that I am going to tell you is, for Lyman series, okay, just concentrate what I am saying, very concentrate what I am saying. What is the maximum energy of this Lyman series? Maximum energy, what will say? Sir, maximum energy is when electron is jumping from infinity to ground state. That means at infinity energy is 0. At infinity energy is 0. And okay, and at ground state energy is minus 13.6. Energy is minus 13.6. So what will say? Maximum, or it is in negative, so you can say that it minimum. You can also say that minimum. A maximum energy when it will come out, it will be 13.6 eV. Okay, so if electron is jumping from infinity to the ground state, at ground state it is having energy minus 13.6. That means the wavelength that came out is 13.6 eV, corresponding to 13.6 eV. So the maximum energy that it will come in Lyman series is 13.6. What is the minimum energy? Minimum energy means, sir, very small, from n equal to 2 to n equal to 1. If electron is jumping from n equal to 2 to n equal to 1, that will be very small. That will be very small. Because if coming from 3, 4, 5 or infinity, that will become large. If you see, this distance is less, very less, then this, other all will increase now. So what will say? Minimum energy is this difference, and which is 10.2, which is 10.2 eV. That means for Lyman series, the minimum energy radiation is 10.2 eV and the maximum is 13.6 eV. Okay, now if you see for Balmer series, maximum when it will be maximum, from infinity to second, from infinity to second. So how much it will be? 3.4 eV. What is the minimum? Minimum, you will say that, sir, when electron will jump from n equal to 3 to n equal to 2, this one will be minimum, this one will be minimum, other all is maximum, 1.89 plus 0.66 plus 0.31. So it is going on adding. So what you will say that What do you say that, sir? Minimum is this 1.89 eV. So now you can see this Lyman series is having maximum energy 13.6, minimum energy 10.2. Balmer is having maximum energy 3.4. That means first all the Lyman series will occur, maximum energy, after that Balmer, after that other. Are you getting my point? So maximum energy, if there is any series in Lyman, that will be having more energy than Balmer, and Balmer will be having more energy than Passion. Are you getting my point? What you pronunciated? PSCHN, passion, anything. Then bracket, then P fund. Are you getting my point? What I'm saying? That Lyman series is going to have maximum energy, whether it is any wavelength from 2 to 1 or 3 to 1 for n or n to 1. Anything is it if it is going to have maximum energy. After that, Balmer, then Paschen, then bracket, then P fund. Are you getting my point? Is it clear? Some values it is very good if you remember some of the values like 13.6, 3.4, 1.51. At least 2-3 values you must remember for H atom only. I'm not talking you about any other, but for H atom, these 2-3 values, if you remember, it is very good. It can be very useful. Now next, one thing is left in this. After that, we will do the questions in next lecture. Wavelength of photon emitted. Now this radiation that is coming out, we have seen about the energy of that radiation. That radiation which is coming is having how much energy? For example, if electron is jumping from n equal to 2 to n equal to 1, the radiation which is coming is having energy 10.2. Are you getting my point? The energy which is coming is 10.2. So similarly, what we will say, wavelength of photon emitted. This photon that is getting emitted, what is the wavelength of that? So what we will say, hc by lambda. The energy that is coming out must be having hc by lambda corresponding to that energy. That must be equal to the energy. So initial minus final. Initial energy minus final energy. What is the initial? If electron is in n equal to, for example, 2. So at that point it is having some energy. I told you, any electron that is moving in any orbit is having energy corresponding to that state, or that orbit. So when n is in n equal to 2, when electron is in n equal to 2, 1 second, when electron was in this, electron was here in second, it is having some energy that is minus 3.4. What it is saying, initial energy minus final energy. Finally electron has came to where n equal to 1. Here energy is minus 13.6. So what you will say, minus 3.4 minus into minus plus 13.6. How much it will be? 10.2. Are you getting my point? So from this, what we are calculating is, from this EI minus EF, what we are calculating is what is the energy of the radiation that is coming out, and then we are comparing it with hc by lambda. So we will get the lambda, wavelength corresponding to photon emission, wavelength corresponding to photon emitted. Are you getting my point? Simple, energy is equal to hc by lambda, nothing more we are doing. Similarly, now here, this energy, we know that total energy 13.6 z square by n square. Are you getting my point? Energy is this only, no, minus 13.6 z square by n square. So by keeping that formula there, putting value of h and everything, we got 1 by lambda. 1 by lambda means 1 by wavelength. 1 by wavelength is equal to r. R is a constant, 1 upon n2 minus 1 upon n1. What is n2? N2 is the state after jumping. N2 is the state after jumping. What is N1? N1 is the initial state. Initially where this electron is there. In which orbit electron is kept. And after jumping, on which state it is coming. That is N2. N2 and N1. If you put the formula here, you will get the answer. What is R? R is Rydberg's constant. What is R? Rydberg constant. Value is 1.097 into 10 raised to power 7 meter inverse. Are you getting my point? 1.097 into 10 raised to power 7. Or you can just 1.1 also you can say 1.1. 1.1 into 10 raised to power 7. 1.1 into 10 raised to power 7 meter. Are you getting my point? So I am again telling you what you have to remember. So here nothing, J.J. Thomson model, nothing you have to remember. Alpha particle is scattering. I told you 99% of the space is empty electron because all the alpha particles are crossing straight. Okay, and only 1 out of 10 raised to power 6 is coming back. So what he said, that all the mass is concentrated in very little space, other all is empty. Other all space is empty. So he gave this model, but he was not able, and he also gave the approximately radius of nucleus, that is 30 Fermi, that is 30 Fermi, 3 into 10 raised to power minus 14 meter, that you have to remember. What are the drawbacks? What are the drawbacks? He said that electron is moving in any orbit, then it must lose energy, radiate and lose energy and become unstable. So he was not able to explain this. Also, he was not able to explain this, that the radiation that is coming out, okay, is of some particular wavelength only. Why it is happening? So this all is corrected by Bohr atomic model. What he said, that electron is moving in a some particular orbit only, in which its angular momentum is equal to integral multiple of h by 2 pi. From that equation and from one equation of your centripetal force is equal to your electrostatic force. From there, from these two equations, we have got a very interesting thing, very important formula, R, V and total energy. R is 0.529 into n square by z. Are you getting my point? Whereas V is equal to 2.19 into 10 raised to power 6 z by n. And total energy is minus 13.6 z square by n square eV. Remember, this energy is in eV. Are you getting my point? What I told you, that this is valid for all H-like atom having one electron. If total energy is minus x, then kinetic energy will be x and potential energy will be minus 2x. Kinetic energy will be potential energy will be minus 2x. I have given you one example also. Then we have defined the ground state, excited state, ionization energy, ionization potential, excitation state, and then binding energy. All this I have told you. After that, I have said you, if energy radiation is occurring when electron is jumping from any state to one, we are calling it Lyman. When electron is jumping from any state to 2, we are calling it Balmer. Are you getting my point? And then energy, I have told you that energy of Lyman is going to be more than Balmer, and then so on. And again, this radiating energy, this photon that is coming out, what will be its wavelength? Then we have a formula, 1 by lambda is equal to R. R is a Rydberg constant, 1.1 into 10 raised to power 7 meter inverse into 1 by n square minus 1 by not as n square, 1 by n2 minus 1 by n1. What is n2? N2 is the state, final state after jumping. What is n1? Is the initial state. Simple. Thank you, sir. We are done here. Now next video I will be giving you the last examples, last questions of last previous JEE mains questions and previous AIMS questions, AIMS and NEET questions. So I will be making different videos, for engineering different, for medical different. So till that, just be safe, be at home, study, keep on studying and growing and watching the classes. Okay, so bye bye, take care.